Hi everyone. We're going to look at the properties of water now, and this is going to be a common theme. We're going to talk about water a lot. It's so very vitally important to life on Earth, and a lot of why it's so important is because of the chemical properties that it has. Okay, this is a slide that we just looked at when we looked at our chemistry review. It shows hydrogen bonds between water molecules. It shows polar covalent bonds between the oxygen and the hydrogen of the same molecule. And because that polar covalent bond creates a slightly negative area, slightly negative area and a slightly positive area, that allows the slightly positive area of one molecule to be attracted to the slightly negative area of another molecule. It creates this sort of stickiness of water and this ability of water to want to hold tight to itself without breaking apart. Okay, so this is what we talk about when we talk about polarity. Is this the idea is that there is a gradient of negative and positive. Okay, it's the same thing like when we're talking about polarity of magnets or batteries. There's a positive end and a negative end. Okay, but it's all down to the unequal sharing of electrons that make the water polar. Now, where this, you can see this all in action at really good is in plants. In the xylem of a plant, any plant, if we're talking about a tree, we're talking about a little baby petunia, all water has to go from the roots and it travels all the way up the plant. Sometimes it's not that great of a distance. Sometimes we can talk about a giant redwood and it's a huge lot of difference, distance, and it has to go all the way out and out the leaves of the plant. So how does water do that? It has to fight gravity. How does it get all the way up there? Well, the answer is in part polarity and hydrogen bonding. Okay, so we have a word that you want to add to your notes called cohesion. This is the attraction of molecules for other molecules of the same kind. And cohesion is because of hydrogen bonds. So when we say attraction of molecules of the same kind, an example is two different water molecules. They're the same kind, right? They're both water, but they are attracted to each other because of the hydrogen bonds together. And it's because of the polarity of the water molecule. This allows water to travel up against the pull of gravity in plants because it's almost like they're holding hands, right? And the one going up first is holding the hands of the one below it, and it's helping them go up the um, root or the xylem of the plant, okay? This is another reminder, cohesion is H2O molecules stick together, right? So it's like little kids holding hands, that's what cohesion is. We talked a little bit about surface tension. So this property, this cohesion, this hydrogen bonding, it's responsible for surface tension. Um, we talked about doing a belly flop in a pool and how when you do that, it hurts a lot because you have a large surface area coming in contact with the large surface area of the water. And because of this hydrogen bonding, it creates this surface tension, and the water wants to resist the force of your belly. So it's a large surface against a large surface, there's a lot of force. But if you make yourself pointy, like if you do when you're a diver, it reduces the amount of surface area that's coming in contact with the water. And so it kind of, you're able to slip through and the force isn't as great, so it doesn't hurt as much as it does when you have a larger surface area coming in contact with the water. All right, so that was cohesion. This is adhesion. This is the clinging of a molecule to a different molecule. So not water attracted to water, water attracted to something else. In this case, water is attracted to the sides or the xylem of the leaf, and it allows things to kind of cling to it and not slide down, right? You always it's always fighting against gravity. Gravity is wanting to pull it down. Well, the fact that water can kind of cling to the sides, and because it can cling to each other, allows it to continue up the xylem without falling back down. So this is again due to the polarity of water, because you have that slightly negative oxygen area and you have the slightly positive hydrogen area. Again, it can interact with other things and it can cling to those things. That is adhesion. So when you have H2O sticking to the xylem or some other molecule, that's what we're talking about when we talk about adhesion. Now, if you take all of that and put it together, take the cohesion, the adhesion, and the surface tension, you put that all together and we call it capillary action. It's basically the movement of water against nature or against uh, gravity or through a tube, and it can be a xylem, it can be even a plastic tube that you have in the lab. Capillary action will act the same way. It occurs when the adhesion is greater than cohesion, and it's very, very important to the transport of water and nutrients in the plants. And so this is showing you the capillary action moving water upwards through the xylem. So it's really just taking all of those forces, the polarity, the hydrogen bonding, the cohesion, adhesion, and the surface tension all together, and we call it capillary action. All right, so now on to some properties of water, okay? Water has unique properties based on its molecular structure. Everything's molecular structure dictates what kind of properties and characteristics it has. Water has a high specific heat, which means that it likes to resist change. It doesn't want to change temperature, go up or go down, and that's because of hydrogen bonds. Heat has to be absorbed in order to break hydrogen bonds, but heat is released when hydrogen bonds form. And because there are millions of breaking and releasing, it tends to stabilize the temperature, okay? This moderates air temperature in large bodies of water, can absorb heat during the day and release it at night. And then it also helps with stabilizing ocean temperature. Organisms, which are made primarily of water, can resist changes in their own internal temperature. Now, that would apply to us, wouldn't it? We are organisms that are made mostly of water, and we can, for the most part, regulate our own internal temperature. We tend to stay at what temperature? Anybody? 98.6. Now, obviously, normal is different for everybody, but it's around there. And regardless of whether we go somewhere where it's hot or we go somewhere where it's cold, our body tends to try to maintain that internal temperature by doing either shivering and firing off those muscles in order to raise your temperature, or by sweating in order to lower the temperature. So there's lots of different ways that your body does um, to do that, but a lot, again, it's because of the properties of water that happens. Okay. Properties of water, we are now talking about evaporative cooling. Water has a high heat of vaporization, just for the same reasons that it has a high specific heat, because of the hydrogen bonding. The molecules with the highest kinetic energy leave as gas. And what happens is that gas leaves and it takes with it heat. Okay, the best example I can give you is when on a hot day you are sweating, and the sweating puts water on the surface of your skin, and what happens then is that water will evaporate from the surface of your skin, and when it leaves as gas, it takes with it some heat. So that's your body's attempt at cooling you down, because as you sweat, it's cooling you down. It may not feel like it all the time, but that's exactly what it's doing. It's trying to maintain a stable internal temperature for you by using that property of water to cool you down. It also is helpful for moderating Earth's climate. That's something that is all due to this nature of water. It stabilizes temps in lakes and ponds because as it evaporates and leaves, it takes with it, again, it takes with it heat. It prevents terrestrial organisms from overheating, okay? Just like in humans, when we sweat, it helps keep us at the internal temperature, the steam. We want to stay around 98.6. We don't want to get too overheated. And so sweating helps us prevent overheating. And it also helps with leaves. When leaves transpire, when water is leaves the surface of the leaves, it takes with it heat as well. So it prevents those leaves from becoming too warm in the sun. All right, finally, floating ice. Water that solidifies, it gets bigger, it expands a little, and it becomes less dense, meaning the water molecules are not as tightly packed together as they are when they're in liquid form. This is because when water cools down to form ice, the molecules start to move really, really slowly. Remember, we said that all atoms are always moving, okay? And in water, they're moving particularly fast. They're forming bonds, they're breaking bonds continuously. Well, when they are moving so slowly because they've been cooled, they can't do that anymore. So it allows them to expand a little bit and not and not hold on to each other as tightly, and it allows the water, or I'm sorry, the ice to float on the surface of liquid water. This allows marine life to live underneath the floating sheets of ice. I mean, you can imagine how bad it would be if you have something that lives on the floor of the ocean, and every time anything ices over, then that ice sinks to the bottom and crushes anything below it, right? I mean, that would not be good. So because of ice floating, marine life is able to survive underneath of it. Hydrogen bonds. Once again, this is going to be a theme throughout this unit, but hydrogen bonding causes a crystalline structure. That means it's usually an ordered structure. Sometimes it's very, very ordered. Sometimes it's not as much. The closer the molecules are able to get to each other, the more solid or more dense the substance will be, and the farther apart they are, the less dense they are. So I want you to imagine a 3D crystalline structure of ice. How many hydrogen bonds can one molecule of water make with its neighboring water molecules? Okay, think about that for a second. We have oxygen. Let's do another color. We'll do hydrogen, and they're bound together. This has got a slightly positive, that's a slightly positive, this is slightly negative because there's two unshared pairs here. So how many hydrogen bonds can it form? One water molecule can bind hydrogen bond with how many other water molecules? What do you think? Take a minute, sketch it out. Don't just guess, think about it. How many bonds do you think it can make? Well, let's take a look at this. This is a positive charge, right? And we said that that positive charge can bond with the slightly negative oxygen. Okay, so this can be one bond. Then we have another oxygen here that's negative that's going to bond. What's tricky is you notice here this oxygen here is bonding with something, right? This oxygen is bonding with this hydrogen. So that means this hydrogen or oxygen up here can also bond. And what you can't really see is that these two electrons kind of form these big Mickey Mouse ears because electrons don't stay in one place. Electrons are always zooming around. And so this would be like their path. Okay, the electrons form this big sort of, we call it the electron cloud, and it's slightly negative. So that means this then is also going to find a slightly positive hydrogen, and this is also going to find a slightly positive hydrogen. So that is 1, 2, 3, 4 other water molecules that every water molecule can bind to. That tends to be why surface tension is so high with water, is because it can form all of these different bonds. We say that water is a solvent, and it's a very versatile solvent. Its polar molecules are attracted to ions, and other polar molecules it can form hydrogen bonds with. That means if you put water on things that tend to form ionic bonds or tend to form ions, it very quickly can dissolve it and pull it apart. Okay, that's what solvent means. It means it is breaking it down. It is dissolving something into its ions or into its elemental form. With any, we call this the S's of chemistry. We have a solution, and the solution is made up of a solvent plus a solute. The solvent is the dissolving agent, is the one that's doing the dissolving, and the solute is the thing that is being dissolved, and the solution is the mix of two substances. So if you have a beaker full of H2O and I put NaCl in it, oops, NaCl is table salt, what is going to happen? That water is going to break down that NaCl. So the NaCl is being dissolved, so it is the solute, the water is the solvent, and the resulting salt water, that is going to be the solution. Okay, so the solution is all of it, the whole system. The solute is what gets dissolved, the solvent is what does the dissolving, and typically, especially when we're talking about biology, we're going to be talking about water as a solvent, because in biological systems, water tends to be the solvent. So like tends to dissolve like. Water can interact with sugars or proteins, and that's because they have lots and lots of oxygens and hydrogens. Okay, and because there's lots of oxygen and hydrogens, then water will form hydrogen bonds with a sugar or protein to pull it apart and dissolve it. Okay, and so that is why water is able to dissolve a lot of things in biology, because what did we say? That most things in the biological world were made up of carbon, oxygen, hydrogen, nitrogen, right? All of these things, H's and O's, okay? Water can dissolve anything with H's and O's, and 96% of all biological systems are made up of these four elements. So by and large, things are dissolvable in water. Okay, ionic compounds. The partially negative oxygen in water will interact with a positive atom, right? Negative is attracted to positive. The partial positive hydrogen will react with a negative ion. Again, positive is attracted to negative. So this shows you an example of sodium chloride. Again, this is salt. And notice that salt is in a very ordered structure crystalline pattern. Salt tends to do that. The positive sodium and the negative chlorine form a very regular pattern, very tightly impacted. But when you put that into water, water starts to, the H's start being attracted to the chlorines, right? Because, oops, sorry, that's not it. The hydrogens are going to be attracted to the chlorine because the hydrogens are positive, and then the negative oxygens are going to be attracted to the sodium. And so once they start forming these hydrogen bonds, they start breaking apart and dissolving all of the sodium and chlorine from each other and creating that solution. So that's basically the process of dissolving something, is having the right polarity, positive and negative, to break apart whatever it is that you're trying to dissolve. Okay, so this is going to be your exit ticket for these note sections. What I want you to do, and I'll put this in a Word document that you will just fill in, but basically I want you to kind of think about what we've been talking about. I want you to describe what you think would happen if you mix potassium chloride with water. I want you to try to be as descriptive as possible. And while we're here, I want you to kind of we want to look at some of these questions. Notice that all of the task verbs are in blue. That is because you really got to get good at looking at a question and really understanding what it's asking you. Okay, and that's why I gave you those task verbs. If you don't have them in your a bill yet because you can't print them out, that's fine. Just pull up that paper and look at the task verbs and look at what does it really mean to describe something. What does it really mean to make a prediction? Okay, so make sure that you're looking at those. But for this, I want you to describe what would happen if you mix potassium chloride with water. Then I want you to draw and label a diagram to justify your explanation. Okay, so just to give you a little bit of chemistry background, if you look at a periodic table of elements, let's go back up here and see if we can't find one that's not, okay, here's one. So it said potassium and chlorine. So what do you notice? Potassium's on the left side, so potassium is a metal, and chlorine's on the right side, so this is a nonmetal. A nonmetal and a nonmetal form an ionic bond. Okay, and so that's where you're coming from when you're answering this question. You got to think about that's the way they're bonding. So what do you think is going to happen when you put them in water? Okay. And when it says to draw and label a diagram, that's what you're doing. You're drawing and labeling molecules, basically, like what we've been doing. Then you're going to identify one property of water that contributes to the suitability of the environment for marine life. What is one thing about water that makes it good for marine life? Then I want you to predict one disruption that would occur in the environment if ice was more dense than water. We know that ice is less dense, but what would happen if it was the reverse and ice was more dense? What do you think would happen? And just by disruption, I mean anything. Something dies, something changes, something doesn't work right. Any disruption in the systems of biology, what do you think will happen? Okay. All right, guys. Until next time, enjoy.